Well, good evening. Welcome to this online lesson in Intermolecular Forces. I'm Mr. Smith. A quick rundown of what we're going to have a look at today. So we're going to begin by looking at covalent bonds, and in particular polar and non-polar bonds, and how they lead to a molecule having polarity or not being polar. It's an important thing that you need to be able to identify, because that is the way that you can determine which intermolecular forces are present between molecules. And then we'll move on to the three types of intermolecular forces and how they are created, how you can identify whether a particular molecule, or sorry, I should say, how you can identify which intermolecular force is a stronger form in a particular molecule. So I'm going to begin very, very quickly just to remind us all what a covalent bond is, because this is a key. We're talking about molecules. These are molecules that are covalently bonded. You might call the covalent bond the intramolecular bond or intramolecular force, whereas in this section we focus on the intermolecular force. It's an important distinction to make. The forces within the molecule, the covalent bonds, are not broken when a simple molecule undergoes change of state. It's the intermolecular forces between the molecules that are themselves broken. So a quick reminder, covalent bond, yes, it's a shared pair of electrons between two atoms. Virtually every A-level student would be able to say that. Sometimes not all A-level students are clear on why a covalent bond holds two atoms together. And it's because you have an electrostatic force of attraction there. And it's an electrostatic force of attraction between the positively charged nuclei and the shared pair of electrons. I just realised this diagram's a little bit misleading because it looks like there are three dots in there. We would have a shared pair, or maybe two pairs or three pairs. You wouldn't have an odd number of electrons. So, because that's annoying me a little bit. Let's see if my chance to just try out my. There we go. So I've just tried to get rid of all of those dots to make the point that it would be a shared pair, or maybe two pairs or something. And it's that attraction. It's the attraction between the pair of the charge negative, of course, and the positively charged nuclei that holds two atoms together when they are covalently bonded. So when it comes to bond polarity, you need to be clear on the definition of electronegativity. It's a frequent one-mark question, this, define electronegativity. The wording can change ever so slightly, but you really need to convey the idea that it's the power of an atom to withdraw electron density from a covalent bond, or to attract electron density from a covalent bond, attract electron density within a covalent bond. That's the idea that you have to get across. And you need to be clear that if you have two atoms of different electronegativities covalently bonded together, then that electron pair will not be evenly shared between the two atoms. You can think of it almost like a tug of war. The two atoms that are covalently bonded are in a tug of war, and the more electronegative atom pulls the shared pair closer to itself because it has more capacity to do that. You are not required to memorize electronegativity values. You are expected to know that the general trend is that they increase from left to right and they increase from bottom to top on the periodic table. The reasons for that are related to increased nuclear charge as you go from left to right, with the same amount of electron shielding as you go from left to right. As you go down, the electronegativity decreases because you have more shielding between a nucleus and a shared pair, and the atomic radius increases as well. Those are things that perhaps be explored if we do a session on periodicity another time. I don't want to dwell on it any more than that for the time being. So just a little bit of background. These are useful rules of thumb in terms of how the electronegativity difference of a bond will affect the type of bond that you get. If it's 0.4 or less, then the bond is considered to be non-polar covalent. So even though there's an electronegativity difference, it's not enough to produce an appreciable effect in terms of polarity. And that's significant because, for example, the carbon-hydrogen bond has a difference of 0.4. although there's an electronegativity difference between carbon and hydrogen, it's not enough to make that a polar bond. If you have a difference of 0.5 to 1.6, then it does become polar, a polar covalent bond. Greater than 2 tends to be ionic. You may have noticed a bit of a gap between 1.6 and 2.0. That's because it depends for that range. If there's a metal involved in the bond, then it would be ionic. Otherwise, it becomes a polar covalent bond. They're just a set of useful rules of thumb to determine whether a bond is going to be polar or non-polar. We'll really focus on the first 2 bullet points here. Is it a polar bond or is it a non-polar bond? 0.4 or less, non-polar. 0.5 to 1.6, polar covalent. So they're the two that we're going to focus on today. So here we go then. This is what we've talked about so far. So we've said that the electron pair isn't evenly shared, and you end up generating a dipole if it is the case. Now what I'm going to try to do is to show you what I mean by this. Hopefully the pen is working okay. So in the case of chlorine, just trying to draw on here now. Sorry, it's just a little bit temperamental. Let's try something a little bit different. Here we go. There we go. So if we put J pair here for chlorine, because those two atoms have the same electronegativity, they're both electronegativity 3.0, that shared pair is going to be evenly shared between the two. In the case of hydrogen and chlorine, though, if we look at hydrogen at the top left of the periodic table, it has electronegativity of 2.1, chlorine is 3.0, that's a difference of 0.9, that would make it polar covalent, which would mean that we would have our shared pair much closer chlorine than to hydrogen, and this creates what we call this polar bond. So chlorine has a greater share of the shared pair, which means we put this delta sign on it. We say that it is delta minus. It has a partial positive charge. The Greek letter delta or Greek D is used to indicate a small amount of something. In this case, a small amount of charge. The hydrogen, of course, will be delta plus. Now, in the case of sodium chloride, if we imagine all of the electrons, all the valence electrons, chlorine has its 6 valence electrons because it's in group 3, 7 valence electrons because it's in group 7. Sodium has the 1 electron because it is in group 1. Rather than forming a covalent bond, the electronegativity difference is so great that the electron is lost completely. You can imagine it as perhaps for an instant a covalent bond is formed. The electronegativity difference is so great that chlorine pulls that pair right towards itself and it keeps it completely. So what we end up with, if we just get rid of what I've done there with chlorine for a little while, the more what we end up with is a situation where chlorine actually keeps the electron completely, so it becomes negatively charged. Sodium becomes positively charged. You have your ionic compound where we formed ions instead. And at GCSE, you would have thought of one thing as being either ionic or covalent. One of the things you have to appreciate at A level is that it's a spectrum of possibilities. It's not one or the other. You have your polar covalent bonds, your non-polar covalent bonds, and also your ionic bonds, and even ionic bonds with covalent character, but they're definitely one to look at for another time. Okay, so just to emphasize the point that I've been making here, in terms of your polar and non-polar bonds, you've got your much bigger electronegativity difference. The hydrogen chloride molecule is going to contain a polar bond, whereas your chlorine molecule is not going to contain a polar bond because of that sharing of electrons. So from polar bonds to polar molecules. First things first, if all of the bonds in a molecule are non-polar, then the molecule itself has to be non-polar. However, if we have a molecule with a polar bond, then that may cause the electron density to be unevenly shared across the whole molecule. That gives the molecule polarity. It's to do with symmetric sharing of the electrons within the molecule. Not just the shared pair, but all of the electrons in all of the shells. And electronegativity, even though that focuses on the shared pair, it can be used as an indication for how all the electrons on each atom are going to be shared across the molecule. So what I'm going to do at this point, I'll actually go back a slide to show you this. So if we consider chlorine here, and hopefully this will work okay, we were to consider the electrons as they are being shared across this molecule. Let's see if I can move that and put it into a better place. So there we go. So if you imagine the oval representing the electron density of the molecule as a whole, then it's shared evenly across the whole molecule. That means that the charge is completely evenly distributed across the molecule. That means that we have a molecule with a non-polar bond, and it will be a non-polar molecule. Now for this one, I'm going to have to draw it. Chlorine has a much greater pull on the electron share than hydrogen because of its increased electronegativity. What that means is that this cloud of electron density is not going to have this perfect symmetrical oval that we have for the chlorine-chlorine molecule. It's going to look more like this. It's going to be unevenly shared. Chlorine has a much greater share. Hydrogen has much less of a share. And that means that the right-hand side of the molecule, where chlorine is going to have this partial negative charge. The left-hand side, where hydrogen is going to have a partial positive charge. But that will lead to a polar molecule. So let's have a look at some more examples here. First of all, we'll begin with water. We have our water molecule here. Oxygen is the more electronegative atom. That means it will have the bigger pull of electron density across the molecule. So again, just like before, we imagine the cloud representing the electron share. Oxygen has a much bigger pull on the electron density than hydrogen does. I think I'm going to redraw that because I'm not convinced that it shows it perfectly. Let's try it again. I think that kind of makes the point a little bit better. So just looking at one bond on its own, oxygen is pulling electron density towards itself more strongly from both hydrogen atoms. As a result of that, we have a lot of electron density at the top of the molecule as it looks where the oxygen is, where the delta minus is, less electron density around the two hydrogen atoms. So we know that the bonds will be polar, but because that electron density is not evenly shared across the molecule, because it is asymmetrically shared across the molecule itself will also be polar in nature. So it's looking for that symmetry. Is the electron density symmetrically shared across the molecule? If the bonds are polar and the electrons density is not symmetrically shared, it will be polar. If the electron density is symmetrically shared in all directions, then even though the bonds are polar, the molecule will be non-polar. What we're going to do now, you can have a go at some of these. I'm going to send you a multiple choice survey. There are 4 options, A, B, C, D. You have to identify both whether the bonds are polar or non-polar, and then whether the molecule is polar or non-polar. So I'm just going to send this out now. So you should have received that. You've got your choice, A, B, C, or D. Are the bonds polar, and therefore is the molecule polar? Click for option, click send. Okay, so we'll get the answer to this first one then. Well, bonds are clearly non-polar because we've got a big electronegativity difference between nitrogen and hydrogen. The electron density is not evenly shared across the molecule. The top part of the molecule here has a big negative charge, the bottom part's are positive charges. That means that this molecule will be polar. A couple more then. This is carbon dioxide. So same as before, I'm going to send the survey out. Your 4 options are there. Here it comes. Give me another 10 seconds. Okay, so this molecule here, well, the bonds are polar. There's no doubt about that. But the thing is, there's no uneven distribution of electron density in this molecule. So as a result of that, the molecule is actually non-polar. So, okay, initial the survey. Yeah, don't worry about it. I will try and send another one. See if it works this time. The way it should work is that you click on the letter and then click send. So we'll try the next one. So we have a molecule here. Just load up the survey. I'll send that out. Here it comes. So just like before, so are the bonds polar? Is the molecule polar or non-polar? Okay, so the answers have come through. Bonds clearly are polar. It's a tetrahedral molecule. We have 4 bonding pairs. That means that they will all repel evenly. So this is a perfectly symmetrical molecule where every bond has equal polarity. The effect of that is that there is no overall imbalance of electron charge anywhere in the molecule, which makes it a non-polar molecule. Just did that one. I've accidentally jumped ahead one, unfortunately. There's no point doing a survey, but I'll just run through it. Methane, in this case, the electronegativity difference isn't big enough to have an appreciable effect. Like I say, I accidentally clicked it ahead on that one, so we'll just go through the answer. The bonds are non-polar, so the molecule has to be non-polar. Okay, so I think this is the last one from this section here, from this set of questions. So again, you have one more molecule. Okay, so the survey has just been sent out. Okay, so the answers have come through. Is this molecule polar or non-polar? Well, will actually be polar because the electron charge won't be evenly distributed across the whole molecule. The 3 chlorine atoms at the bottom are all pulling electron density towards themselves, and as a result of that, we'll be pulling electron density slightly away from the carbon-hydrogen bond 2. So although the shape of the molecule is symmetrical, the electron distribution will not be even. Looking at it from top to bottom, the hydrogen atom will have a slight positive charge as a result of that. But if all the atoms that join to carbon are the same, then it will be non-polar even if the bonds are polar. But if you change one of those 4 atoms for anything with different electronegativity, that will result in the electron density not being shared evenly across the molecule as a whole. Okay, so what we're going to do now is move on to intermolecular forces. We have the example here with chlorine molecules. We've already established that these chlorine molecules have what we would call even electron density across the molecule. So I'm going to try to represent that by using oval shapes to represent the electron density across the molecules. Hopefully they'll be at the same size. I'm drawing them as we go. So here are our three regions of electron density, and these are non-polar molecules with non-polar bonds because the electron density is completely evenly distributed across the molecule. Well, that is the case on average. What will actually happen is that if we take the molecule on the left-hand side, and I'll try and show you what the heck is working real time. I'm looking at my dummy screen. Seems to be working okay. The electron density will randomly shift ever so slightly. Now, these slight shifts occur in fractions of seconds, literally fractions of seconds. They are instantaneous in nature, and they occur, and the electron density moves on very, very quickly, literally in a fraction of a second. If we have a situation here where just for a fraction of a second, the electron density on this left-hand molecule has moved away from the atom on the left and it's towards the atom on the right, the result of that is that we do actually form a dipole where the atom on the right-hand side of the left-hand molecule will have a delta minus charge, and the atom on the left will have a delta plus charge. The result of that is that the molecule to the right, its electron density will be repelled. So we have what we call a temporary dipole in the molecule on the left-hand side, and this will cause on the right-hand side a dipole to be created or induced. And this is why these particular intermolecular forces are known as temporary dipole-induced dipole forces. And the molecule on the far right will also experience the same effect. Its electron density will also, for this fraction of a second, find itself actually being repelled. A fraction of a second later, the electron density on the molecule on the left will have shifted, and that will cause shifts in other molecules. The ones in the middle or on the right might undergo a random shift. And the result of all this is that you get these what we call temporary dipole-induced dipole attraction forces forming here between the molecule. It's what we call them, temporary dipole-induced dipole intermolecular forces. Just bring the annotation back up again just for a second, because I realise I've moved off that very, very quick. Like I said, we call them temporary dipole-induced dipole intermolecular forces. A very, very long-winded, unhelpful name. So we don't use that name. We actually call them van der Waals forces, after one of the scientists who did a lot of the work in terms of explaining how these forces are created. They are present between all simple molecules, not just the non-polar ones. This is something that's often missed. These intermolecular forces are present between all molecules, all of them, whether they have a permanent dipole or not. In all molecules with permanent dipoles, the electron density is not static. It shifts. It moves around. So these forces occur between all molecules. They get stronger as the molecule or atoms, because they occur between atoms of noble gases as well. They get stronger as the atoms or molecules get larger, quite simply because the larger the atom or molecule, the more electrons there are to undergo a shift in density. So this is why you may have seen the boiling points of, say, the noble gases. They do increase as you go down the group. for example, here are some examples of some molecular species. These are the hydrides of group 5. They are all covalent in nature. And what happens is that you see a fairly trend there, where as the molecules get bigger and bigger, the electron clouds around the molecules get bigger, which means that there is more scope for distortion of that cloud by temporary dipole-induced dipole interactions, that the van der Waals forces get bigger as you go down the group 4 hydride. Okay, so the next set of intermolecular forces, well, in this case, we have molecules that have a permanent dipole. This means that by a matter of fact, the electron cloud is not being evenly distributed across these molecules. Chlorine has a much bigger share, hydrogen much less of a share. So we have a permanent delta minus and a permanent delta plus. We have intermolecular forces between the molecules. In many ways, these are much more straightforward. There's a positive part of the molecule, there's a negative part of the molecule. They will attract, just like opposites attract. As I said before, you still get the random shifts in electron density as well, which cause the temporary dipoles that cause induced dipoles on other molecules as well. But these particular molecules, these polar molecules, will also have additional intermolecular force. So what do we call this molecular force? We call them permanent dipole forces or dipole-dipole forces, as they are frequently referred to, dipole-dipole forces. And they are present between all polar molecules. All polar molecules experience dipole-dipole forces of attraction. Now, the important thing to remember about dipole-dipole forces is that they are stronger than van der Waals forces. They're stronger because in the case of van der Waals forces, the dipoles are smaller and temporary. They tend to be smaller, it depends on the size of the molecule, but they're temporary, fleeting, they're not there for very long. Whereas these dipoles are permanent dipoles. So they are stronger intermolecular forces than van der Waals forces. So what we have here are some more hydride graphs. We have the hydrides of group 5, group 6, and group 7. And as you can see, again, they gradually increase as you go up the graph. They are all, I think, on average greater than the corresponding group 4 ones, because here we have a permanent dipole force. And you would expect them to increase as you go down the group, because we've got the molecules. So you've got the dipole-dipole forces and the van der Waals forces increasing as you go down the group, because we have big molecules. You'll notice that I've left a gap on the graph here. I have left out the hydrides from period 2, namely H2O and H3HF. So they are the hydrides group 5, group 6, group 7 from period 2 of the periodic table. Now, if the trend holds, then they should be even lower than the ones that you see on the graph. However, when you actually check them, they are much higher. This clearly means that there must be some additional intermolecular force at play here. There must be something else going on for these 3 particular molecules. They must have an additional intermolecular force above and beyond the van der Waals and the dipole-dipole forces. There's something else there. What is that something else? It's what we call the hydrogen bonds. Hydrogen bonds are a special case of dipole-dipole intermolecular force. These only occur is when a hydrogen atom is covalently bonded to oxygen, nitrogen, or fluorine and they occur between that hydrogen atom and a lone pair of electrons on an atom of oxygen, nitrogen, or fluorine. So the hydrogen atom has to be covalently bonded to oxygen, nitrogen, or fluorine. The other atom isn't necessarily bonded to hydrogen as well, but the hydrogen atom must be covalently bonded to oxygen, nitrogen, or fluorine. But just to give you an example of what I mean, here is ammonia. Here is the lone pair on the nitrogen atom. I'm going to put in a second ammonia. I'm doing this. I think I've already prepared this on my slide. No, I haven't. So if we have a second molecule of ammonia, which I'll just throw in now, then it's a lone pair on the nitrogen atom forms your hydrogen bond just there between that lone pair and between the hydrogen atom, which itself is covalently bonded to nitrogen. Now, I have to point out, as I said before, the hydrogen atom involved in hydrogen bonding would be covalently bonded to nitrogen, but the atom that it interacts with doesn't actually have to be covalently bonded to hydrogen. So, for example, ammonia could form a hydrogen bond with a molecule like methanol. So here's methanol, an aldehyde. It has an oxygen atom, which has lone pairs, and that lone pair on the oxygen atom can hydrogen bond with a hydrogen atom that's covalently bonded to oxygen, nitrogen, or fluorine. The hydrogen atom must be bonded to oxygen, nitrogen, or fluorine, but the atom it's hydrogen bonding with, in this case the oxygen atom on this methanol molecule I draw at the bottom, that doesn't have to be covalently bonded to oxygen. Again, it's a minor point, but it's one that's sometimes missed. So this is hydrogen bonding, special case of dipole-dipole intermolecular force. And it occurs for the reasons I said before. You have to have hydrogen that is covalently bonded to oxygen, nitrogen, or fluorine, and that hydrogen atom interacts with the lone pair on another molecule of oxygen, or another atom of oxygen, nitrogen, or fluorine on a different molecule. So you need to know about the comparative strengths of the intermolecular forces. Hydrogen bonding is the strongest, and the evidence is on the graph that I showed you before, that the hydrides of oxygen, nitrogen, and fluorine have much higher boiling point than the hydrides of the comparative hydrides of the same groups, but of larger molecules. Dipole-dipole forces are the second strongest, and van der Waals are the weakest. Okay, so some more questions then. You've got the molecule, you've got the shape. Your task is to determine which intermolecular force will be the strongest one present. You have to go through as a hierarchy. You know they'll all have van der Waals. So the first step then is, will it have dipole-dipole interactions, yes or no? The answer is no, then the answer is the strongest force of van der Waals. If the answer is yes, then you've got to see whether its permanent dipole will qualify hydrogen bonding, to have hydrogen that's covalently bonded to oxygen, nitrogen, or fluorine. So I'm sending out the first survey now. What is the strongest molecular force in the molecule? So in this case, clearly it meets the criteria for hydrogen bonding because we have hydrogen covalently bonded to oxygen. It can hydrogen bond with itself. So here is the next one. Again, it meets the requirement for hydrogen bonding because we have nitrogen covalently bonded to hydrogen. It can hydrogen bond with itself. Here's the next one. Well, the bonds are polar, but the electron density is evenly shared across the molecule. It's a non-polar molecule, so the strongest intermolecular force has to be van der Waals. It doesn't have dipole forces, therefore it cannot possibly have hydrogen bonds. Here is the next one for you to have a look at. So clearly here, another non-polar molecule. So strongest intermolecular force has to be van der Waals. Next one. Again, another non-polar molecule. Strongest intermolecular force will be van der Waals. And I think I personally jumped ahead to the answer, or my slide hasn't quite worked. So it's a bit of a giveaway, unfortunately, but never mind. You remember this one from the previous time. The electron density isn't evenly shared across the molecule, so it could have dipole. It will have dipole intermolecular forces. It does not qualify for hydrogen bonding because we do not have hydrogen covalently bonded to oxygen, nitrogen, or fluorine. It can't hydrogen bond with itself. Okay, so we're going to finish off this session then by having a look at a past paper question that was on the paper very recently, just last summer, I think. 6 marks for this question. The candidates were provided with 3 molecules. There were some previous parts of the question before this, but the part that concerns us in terms of intermolecular forces is take the relative boiling points of these 3 compounds from the highest to the lowest, justify the order in terms of intermolecular forces. So the stronger the intermolecular forces, the higher the boiling point. We're told that they all have the same relative molecular mass, so they should have very, very similar numbers of electrons. So we know that their van der Waals forces will be very similar in strength. The question is, which one or 2 of them have dipole forces, and just one of them will be able to have hydrogen bond. I think the fact that there are 3 molecules should point you towards one having van der Waals only, one having dipole, and one being capable of hydrogen bonding. That will give you a clear difference between the 3. So then, one last question. Well, one last question in 3 parts. Can you determine the strongest intermolecular force present in each of these molecules? That is the key to be able to answer it successfully. So the survey has gone out. Starting with propanol, intermolecular forces in propanol. Well, we look at propanol. It has oxygen, but the oxygen is not covalently bonded to hydrogen. It cannot hydrogen bond with itself, but that carbon-oxygen bond is polar. Electron density is not going to be evenly distributed across the molecule because it's at one end of the molecule. So that clearly is going to be dipole-dipole. So if our initial thinking is correct, that one will have van der Waals only and another will have hydrogen bonding, then you should be getting a picture of perhaps where propanol will come in terms of boiling points. But then the next molecule, propanol, which will be the strongest intermolecular force present in this particular molecule? Well, propanol has E1, I should say, as its oxygen atom. The oxygen atom is covalently bonded to hydrogen. That means it will be capable of hydrogen bonding with itself. Finally, butane, which will be the strongest intermolecular force present in butane. Well, clearly, butane does not have a permanent dipole of any kind, so the forces that will be the strongest in butane are just van der Waals. They're the only intermolecular force present in butane. Okay, so if those are the intermolecular forces present, then it stands to reason that propene-1-ol will have the highest boiling point of the three, followed by propanol, followed by butane. So here was the mark scheme for this question. 6 marks available for this question, and what you need to do is look at the box. Begin with the box in the middle called level 3. To achieve a level 3 mark with 5 or 6 marks, you had to get the relative order of all 3 correct. You had to identify the strongest intermolecular force in all 3, and you had to use you had to explain the answer coherently, logically, using correct terminology. So you had to essentially explain, go into a little bit more detail, and try to sort of explain maybe why propene-1-ol has hydrogen bonding by referring to the fact that you have an oxygen atom covalently bonded to a hydrogen atom, which propanol doesn't. That would really secure you the 6 marks. So a mistake was made where, say for example, butane was identified as having van der Waals, but the intermolecular forces for the other 2 molecules were perhaps put in the wrong order in some way. If 2 molecules were compared correctly, and the strongest intermolecular forces were put incorrectly, it was still possible to get 3 marks or maybe even 4. But it's not the end of the world if one's in the wrong order. If you get 2 of them in the correct order and you refer to the correct intermolecular forces for those 2 molecules, then that would be okay. So let's just say, for example, you said that van der Waals, propene-1-ol will have a high boiling point with hydrogen bonding, and then said something like, what was it? Propanol will have the highest because that also has hydrogen bonding. The comments on propanol will be ignored, but the comparison between propene-1-ol and butane will be accepted. So that would be okay. Another point worth making, if you look at towards the top, part P, 3rd bullet point down, use of or indicative. You can use those terms, but what you should do is write them out in full the first time you mention them. So the first time you mention them, refer to van der Waals, write it out. First time you refer to dipole forces, write them out, okay? And then after that, you can use VBW or dictate. IMF is accepted as an abbreviation of intermolecular force. Again, a good idea to write it out in full, maybe the first time. And H-bond, again, is allowed as an abbreviation, but I would also write it out as hydrogen bond the first time. So you can use abbreviations to say fine, as long as they are correct, and I would always strongly recommend writing the name out in full the first time, so that is clear to the examiner that you know what is what. Okay, so just to conclude then, one last thing to consider. This is what the examiner said. 4.3 provided proved challenging and discriminated well. That's good news for an examiner. Examiners, the people who set these questions, they want to differentiate between students to see who deserves the A grade and who deserves the B grade. And this question did that very well. Test students can identify the correct order of boiling points, identify the correct intermolecular forces, and use good language to communicate this in a structured way. Many students could identify van der Waals force in butane, yes, hydrogen bonds in propylene monols. You could identify permanent dipole forces in propanol. Indeed, many students mistakenly call that propanol hydrogen bonding. In addition, many students referred incorrectly to breaking of covalent bonds and referred to strength of covalent bonds rather than concentrating molecular molecules. And that takes us back to what I said earlier in this session. You have to be very careful with your terminology. It's the forces between molecules that are broken, and while these substances undergo a change in state, it's not covalent bonds within the molecules that are themselves broken. That concludes today's lesson. I hope you found it useful. If you have any questions for me on the session, you can email me at info@Onlinechemistrytutor.net. Any feedback can also be sent to that email address. Like I say, I hope you found this useful. Hope to see you again soon.